Welcome back from spring break, everybody. We are doing sections 5.3 and 5.4. They're essentially the same topics. Your textbook splits them into two sections, but they really go together, in my opinion. Today we're working on what's called the sum and difference identities. Again, the formulas are always on the front page of your notes that I already gave you, and then we'll hop into the actual notes section. We're working on the sum and difference identities and these co-function identities today. So let's look at them and break them down for a little bit. These are the functions we're working with, the sum and difference identities. I guess you can't really see that. And the co-function identities. I'll put a little box around that since my highlighter didn't quite show up. The sum and difference identities, if we just learn how to read these three formulas, well, there's actually 6 formulas. It's literally just a plug stuff in sort of day. I do recommend, actually I'm thinking about it, if you have your unit circle from algebra, no wait, when did we do the unit circle? This semester? Yes, when we did the unit circle, I would have that out. That's a good resource for today, make part of the questions pretty easy. But what we're going to be doing for these identities is we're going to be evaluating the sum or the difference, that's what it's called, sum or difference, of two angles. So like let's say we're doing the sum of pi over 3 plus pi over 4. That means pi over 3 will go everywhere there's an A, capital A for angle here, and pi over 4 will go everywhere there's a capital B. So for the sine function, if we're doing the sine of A plus B, the formula is sine of A cosine of B plus or minus sine of B cosine of A. Now this is not like the quadratic equation plus or minus where you have to do both. You actually need to choose one. So right now, maybe take a highlighter if you're a highlighter person. I want you to highlight the fact that this says plus minus and this one says plus minus. Do we see that? Underneath it is cosine. Cosine of a sum and difference has a slightly different formula. This time for plus minus in here, you notice it says cosine A cosine B minus plus sine B sine A. That is not a typo. That is an on-purpose symbol. What do you think the difference between plus minus and minus plus is?
I think we made a mistake.
So basically, if you are adding for sine, see how this is on top? You will add in the formula. If you're subtracting, you will subtract. So if you are adding here, what are you going to do? And if you are subtracting here, what are you going to do?
That's opposite.
It's like top goes with top and bottom goes with bottom. We just take two formulas and we smush them together because they're the same other than the symbol.
Wait, so the top one, if you add, you add on the other side, and then you subtract, and and then the bottom one, you add, you subtract, and you subtract, you add. See, this is what I mean. I need to see you talking.
Well, you picked a good spot to sit in. So again, these are the sum and difference for sine and cosine. So we do also want to make sure we're reading this part. If we're taking the sine of a sum or difference, you're using this formula. If you're taking the cosine, you're using this formula. If you're taking the tangent, you're using this formula. Notice that we have the symbol there again. I have the plus minus symbol here. So let's do the pluses first, everything on top, which means that we are going to do tangent of A plus tangent of B all over 1 minus tangent of A times tangent of B. If we are doing subtracting here, the difference of two angles, we will subtract on top, but we will add on bottom. Do we see how to read these formulas? That's pretty much the main gist here. After that, if you can follow the order in which they are listed, that would be great. To help you out, I recommend this color scheme. Let's go ahead and highlight all of the A's in all of these formulas, pink, in all of them, so we can follow the angle A. That's your first angle that you're either adding or subtracting. And then I'm using blue for B. Doesn't really matter the color scheme here, but just so you can see what angle is being used when. The co-function identities, I'm just going to go ahead and talk about this now since we're on this page. We are also going to use them in this section. These should make sense to us. There are co-functions, which I believe we discussed before. Sine and cosine are co-functions. They differ by 90 degrees, and if we're working in radians, that's pi over 2. So Sine of pi over 2 minus theta is equal to cosine of theta. Difference of 90 degrees. So sine and cosines go together. Tangent, cotangents go together. And then secants and cosecants go together. So there's a relationship between them. It all has to do with a 90 degree or a pi over 2 angle. We will get to those eventually. That's where I'm looking when I start talking about the cofunction identities. Can I show you what one of these problems, though, is going to look like going back to the sum and difference identities? You don't have a choice. We're doing it anyway. So now we're going to this page. We're going to be finding exact cosine or sine function values, okay? These are not things that are actually on your unit circle, but I don't want you to put them in the calculator because the calculator is going to return to you a decimal that's like unrounded, and I don't want that. I want the radical answer. I want the exact answer, no rounding. So here's how we do it. We need to think about how to make 15 degrees out of angles that you do know from your unit circle. So what angles are we pretty confident about in our unit circle? Maybe look at quadrant 1. 30, 45, 60. Can we make 15 by adding or subtracting the numbers 30, 45, or 60? Yeah, by doing what? 60 minus 45 or 45 minus 30, doesn't matter. Both of them will work. I'm going to do 45 minus 30 just because that's what I have written on my paper. So we can say the cosine of 15 degrees would be the exact same as the cosine of 45 degrees minus 30 degrees because 45 minus 30 is 15. But now I have angle A and I have angle B to use my formula. I know you'd have to flip back and forth to your formula sheet, so I'm going to go ahead and give this one to you. The cosine of a difference of two angles will be the cosine of the first angle times the cosine of the second angle plus the sine of the first angle and the sine of the second angle. Again, you would look this up on the front of your page. Notice that since I'm subtracting, I'm adding. For cosines, they go together. Cosine, cosine, sine, sine. Here's where your unit circle gets to be very helpful. Those of you with a unit circle out on your desk, what is the cosine of 45 degrees? Square root of 2 over 2. We know this one already. We didn't know 15, but we know 45 degrees. What about the cosine of 30 degrees? Radical 3 over 2. Cosine is the first coordinate, yes. Okay, and then I'm going to add the sine of 45. What is the sine of 45? And then what is the sine of 30? 1/2. Okay, so all I need to do is multiply these fractions and then add them together. This is why we've spent some time previously in this course talking about fractions. How do you multiply fractions together? Ooh, that's dividing fractions. That's adding them. Multiplying is the easy one. Top with top, bottoms with bottoms. Since these numbers are radicals, luckily they're the same radical. They're both a square root, so we can just multiply that number underneath the square root. This one becomes square root of 6 over 4, because 2 times 2 is 4. The second one, square root 2 times 1 is square root 2, and then 2 times 2 is 4. Oh, isn't that nice? Because they have the same denominator, we can already add them together. You cannot add radicals together unless they are entirely the same, which means this numerator just becomes square root of 6 plus square root of 2, all divided by 4. That is the exact answer for cosine of 15 degrees. The trick with these problems is figuring out how to make the number I care about, 15 degrees, out of the things you do know on your unit circle, and then just plugging and chugging in the formulas. Feel okay?
Yeah.
Let's make it harder. We're not stressed, except that we're going to do this now in radians. So this one is a little bit tougher only because using decimals to create different numbers, way easier. You almost immediately knew 45 minus 30 or 60 minus 45. How in the world do we make 5 pi over 12 out of values we know from the unit circle? Thank you so much for asking, right? Here's what we're going to do. We're going to list out the angles that we have in radians on our unit circle just to make this easier for ourselves. This would probably be something I would put on my front page later. But for right now, we're going to list out all of these angles. These are the quadrant 1 angles. You have your 30 degrees, 45 degrees, 60 degrees, and 90 degrees. I just have them in radians. And I want them all to have a denominator of 12 because I want to be able to match the denominator in the question. How do you write pi over 6 with a denominator 12? Multiply by 2. So this is 2 pi over 12. How do you make pi over 4 with a denominator of 12? times 3. So this is 3 pi over 12. See what I'm doing? If I write this one with the denominator 12, it's 4 pi over 12. And if I write pi over 2 with the denominator of 12, it's times 6. So this is 6 pi over 12. Once I have this reference here of knowing what the angles in radians are, except give them a denominator of 12, do you see that there's a way I can add or subtract the divide by 12s to make 5 pi over 12? Yeah, which ones can I add together? I want to make 5 pi over 12. Pi over 6 and pi over 4, right? Because 2 plus 3 is 5. So I can make 5 pi out of 12 out of adding these. So I'm going to go ahead and say that this is actually the cosine of pi over 6 plus pi over 4. That's going to be a difficult moment here, figuring out how to make that number. And now it's just plugging and chugging. So we're going to go back to the formula. The cosine of a sum of two angles. Cosine means that cosines go together and sines go together. So this is cosine of the first angle, cosine of the second angle. Do I use a plus or a minus? Minus, very good. And then I'm going to do sine of pi over 6 and sine of pi over 4. So glad y'all have your unit circles out, because now I'm just asking to evaluate these little pieces. What is the cosine of pi over 6? Mm-hmm. You mean square root of 3 over 2? Because yes? Yep. And then the cosine of pi over 4? Square root 2 over 2? And what is the sine of pi over 6? 1/2. And then the sine of pi over 4? And so again, these numbers are going to start to look familiar to you because we're going to get this kind of pattern recognition down, which is nice. You can generally check your work, be like, I got something way off of this. But we go ahead and multiply the top. Square root of 3 times square root of 2 is square root of 6. 2 times 2 is 4. I'm going to subtract 1 times square root of 2, which is square root of 2 over 4. Since those are common denominators, I can just subtract the numerators together, but can't simplify those. So square root of 6 minus square root 2, all divided by 4, is the exact answer for cosine of 5 pi over 12. What's nice about this is you can throw this in a calculator and make sure that this evaluated correctly. So in fact, let's go ahead and do this real quick, just so you can see that you can always check your work here. Let's do degrees first. So change your calculators into degree mode. Type in cosine of 15, press enter. Save that number in your head or on your screen. And then I want you to come down here and type what we got. We should theoretically have the same decimal approximation number show up on our calculator when we do cosine of 15 or this number. So you can always check your work here. But don't give me the decimal approximation. That's not what I want. I wanted an actual answer, an exact value. Are we cool? Can we try another one so you can start to see this process?
Why not?
Okay, cool. You have these values over here. You're going to need them. I can't show them all at the same time as showing the next problem. So you did write this down, yeah? Okay. So now we're going to make tangent of 7 pi over 12. What two angles can I use to add or subtract and make 7 pi over 12? Am I adding or subtracting them? Adding. So this is actually like doing the tangent of pi over 4 plus pi over 3. The order in which you write them does not matter for addition, FYI. Okay, cool. So let's look at the tangent formula. I know it's on the page of your notebook that's probably closed, so let me go ahead and tell it to you. The formula for tangent is the tangent of the first angle, same sign, tangent of the second angle, all divided by 1 opposite angle of tangent of the first angle times tangent of the second angle. Again, this is just filling in the formula from the front of your page that you have closed. I realize that it's kind of far away from you. So we have our first angle plus our second angle, And then 1 minus the first times the second. Cool. Unit circle time. Tangent of pi over 4. 1. Tangent of pi over 3. That's nice. Okay, then I have 1 minus, and then we've already said these, so tangent of pi over 4 is 1, and tangent of pi over 3 is square root 3. Now that feels extra. What is 1 times square root 3? Square root 3. Okay, so I'm gonna go ahead and show that step. I will not require you to show me that step if you know that's what's going to happen. But what I will require is that you rationalize your denominators. The rule still stands that we are not allowed to leave square roots in the denominator. So to get this to not happen, you are going to multiply the top and bottom by the conjugate of the denominator. Does anyone remember what a conjugate is?
No.
You change something about it. The sign. We change the sign. So I'm going to multiply the top and bottom here by 1 plus square root 3. Because it's the opposite of the denominator, right? Pretty much the same, just change the sign. When we multiply this, the top is going to expand kind of large because we're going to do 1 times 1, which is 1. 1 times square root 3, which is square root 3. Square root 3 times 1, which is square root 3. And square root 3 times square root 3, which is 3. I FOILed that. We FOIL the bottom. 1 times 1 is 1. 1 times square root 3 is positive square root 3. Negative square root 3 times 1 is negative square root 3. A negative square root 3 times square root 3 is negative 3. What can simplify here?
Just positive square root 3's and base 8.
The 3 over negative 3. Cancel.
A lot of things can happen. We can cancel the denominator square roots 3 because one of them is positive, one of them is negative. You see how there's a whole bunch of whole numbers there? I have 1 plus 3 on the top. What's 1 plus 3? 4. And then I have square root 3 plus square root 3. 2 square roots of 3. So it's 2 square root 3. There's 2 of them. What's happening in the denominator now, though? Negative 2. Now, since all of those numbers are even, not this one, can't touch him, it's inside of there. But since this is an even number, this is an even number, and this is an even number, you can go ahead and divide those things, which means that this final answer should be negative 2 minus square root 3. That's the exact answer I'm looking for. If you're like, where did that come from? 4 divided by negative 2 is negative 2, and 2 divided by negative 2 is negative 1. Can't touch the thing inside the square roots because it's not also a square root. Can I give you one to try?
No.
I'm going to do it anyways. Sine of 75 degrees. Look at degrees. Oh, you're so welcome.
Oh, yeah.
Sine of 75 degrees. Give this one a shot. See what you got. So if you did 45 plus 30, don't change it. It's going to end up being the same, if that was what your Odanga was about. So we are doing sine of a sum. So we look at that formula. That formula has sines and cosines mixed and matched. And then you make sure that both angles get both signs, if that makes, or both functions.
Sine 45 and cosine 30, that's still okay?
Yes. Because we'll eventually get to the same spot. So once we get here and we've expanded it into the formula, I look at my unit circle. The sine of 30 degrees is 1/2. The cosine of 45 degrees is square root 2 over 2. The cosine of 30 degrees is square root 3 over 2, and the sine of 45 degrees is square root 2 over 2. When we multiply, we end up with square root of 2 over 4 plus square root of 6 over 4, which we can add together all as 1. So it's square root of 2 plus square root of 6 over 4. And just because I already know this is going to be a question, yes, that is exactly the same as square root of 6 plus square root of 2 over 4. Addition can happen in any order. If that was a subtraction, that's not the case. But addition, like multiplication, can occur in any order. How did we do? Fabulous. Okay, so what if it's already expanded? One of the other things that you'll see in E and F, those examples here, is that I've already written it in the expanded form. What we're going to hope is that when we add these numbers or subtract these numbers together, we'll get one of the angles from the unit circle that we can answer easily. So if I was doing this one, Let's answer a few questions first. What is the first angle? Angle, 87 degrees. What is the second angle? Am I using the sum or difference of sine or cosine? Of. You fell for my trick. Since there's a minus here and it's cosines, so it should be the sum of these numbers together. Because the cosine means that it's a cosine formula. But we're going to go back a step. We're going to say, well, this obviously must be cosine of 87 and then something 93. And since there's a minus in the formula and this is cosine, this is a plus when you start to condense it. They should be opposites. Well, what is 87 plus 93? 180. Don't we know the cosine of 180 degrees on our unit circle?
Yeah.
What is it?
Pi. No.
-1. Ta-da.
Oh, that was
Redo.
Redo? You don't trust me?
No, I need you to explain it.
Okay. These are the angles. So here are the angles.
All right.
Cosine, cosine.
All right.
That tells me that this is going to be cosine. If it mixes and matches, if this said sine and cosine, that's sine.
Okay.
If it says cosine, cosine, that's cosine. Then we also know that cosine is the one that has the funky symbol. So if there's a minus here, that means it came from a plus.
And then you add it?
And then I just added those numbers. 87 plus 93 is 180. Cosine of 180 is -1.
Okay.
Okay? So I'm waiting. Oh, sorry. Let's follow that same thought process on this next problem. What is the first angle?
Sine.
Angle.
Oh, 40.
40 degrees. What's the second angle? 160. Is this going to be cosines or sines?
Sine.
It's going to be sines. Why? Because it's mixed and matched. Cosine and sine, cosine and sine. Okay. So I know that this is going to be the sine of 40 degrees and then something 160 degrees. Is that something a plus or a minus? Minus. Very good. So we are subtracting these things. Interesting. What is 40 degrees minus 160 degrees? -120 degrees. Now here's an interesting moment. Throws it back to what we did before spring break. We had an identity called the even-odd identities. Those of you who have your formula charts out, if you're taking the sign of a negative number, what is that equal to?
Negative sign.
The negative sign. So using the even-odd identity, I can just essentially pull that negative out from the inside, make it on the outside, and just FYI, this is from the even-odd identity, just so we don't forget how that happened later. Well, 120, that's an angle that's on your unit circle. What is the sine of 120 degrees? And then since we're doing the negative, this ends up being negative square root 3 over 2 because it's negative sine of that. Very good. Hooray. No. So the next thing that we're going to work on is using the cofunction identities. Again, sine and cosine go together. Tangent, cotangent go together. Secant, cosecant go together. So what we can do is we can find one value of theta or x that satisfies each of the following. If we have cotangent of theta, equal to tangent of 25 degrees, I know that there's a relationship from my table between these two things that goes like this. It says that if you have the tangent of, it says pi over 2, but that's 90 degrees, minus theta, that is equal to cotangent. That is equal to cotangent. This is just straight up the formula from that row of the formula chart. I changed the pi over 2 to 90 degrees. So that means that cotangent and cotangent can be substituted for each other. So I can rewrite this formula as tangent of 90 degrees minus theta equal to tangent of 25 degrees. Because if cotangent is equal to both of these things, then it's equal to itself. So I have tangent of 90 minus theta equal to tangent of 25. See how there's a tangent on both sides? Let's get rid of it. That just means we're trying to see how 90 degrees minus theta could be equal to 25 degrees. Let's solve for theta. What do you have to subtract from 90 to get 25 degrees? Too much? 65. So theta is equal to 65 degrees. Ta-da! That's it. So you identify which formula you're using. That's what I have in orange. And then you substitute basically the side that's like boring, the side that has theta in it. Substitute that for each other, and you can solve for the angle theta. Your formula chart says pi over 2, right? Not on your unit circle, the front page formula chart.
Wait.
Cofunction identities. See all of them? It says pi over 2. 90 degrees is pi over 2. So if they're using degrees, we use 90 degrees. If they're using radians, we use pi over 2. Those are the same value, different type of measurement. Great question. Let's try this next one. So we're going to use the side that's boring, which means we want the boring side to be sine of theta. On that formula chart, changing it to degrees, we would know that the cosine of 90 degrees minus theta will be equal to sine of theta. That's the formula from the cofunction identities portion of your formula chart. But since both of these things are equal to sine of theta, we can just basically get rid of the sines of theta part and say cosine of 90 degrees minus theta will be equal to the cosine of negative 30 degrees. But now that they match cosines, it's like we're undoing the cosine part. They're only going to be equal if their arguments are equal. So you get rid of the cosine. That's not mathematically a thing, but you get what I'm saying. We're setting their arguments equal to each other. And we're solving for theta. Let me show you some solving steps in case you're like, where did 65 come from? Here's what we're doing. We're isolating theta. We're subtracting 90 from both sides. This becomes negative theta equal to negative 120. If negative theta is negative 120 degrees, what is theta? Positive 120 degrees. So I'm just solving at the last little bit there for theta, once you identify which cofunction identity you can use. Example C. Cosecant of 3 pi over 4 equal to secant of x. The boring side is the secant of x. That's so rude of me to call it boring, but you get what I mean, right?
Yeah.
Okay, so if we look at our cofunction identities for the other one that says secant of x, it says the cosecant of pi over 2 minus x, I know it says theta, but I'm changing it to x, is equal to secant of x. Now I can set the cosecants equal to each other. This becomes cosecant of 3 pi over 4. I guess I should put that in the same order I'd been doing all of these problems. Sorry. Pi over 2 minus x equal to cosecant of 3 pi over 4. If the functions are equal, their arguments must be equal. So I can set pi over 2 minus x equal to 3x over 4. Yep, 3 pi over 4. And I'm going to solve for x. Let's show some work on this one. What would I do on both sides to start to isolate x? Subtract pi over 2. When I go to do that, I'm going to show my work sideways because fractions. But I'm not going to put pi over 2. What do you think I should put down here so I can actually subtract these things? Not pi over 2. They need to have a common what? So I'm going to make this denominator 4. What would be the numerator? 2. What is 3 pi over 4 minus 2 pi over 4? 1 pi over 4. Very good. And if negative x is pi over 4, what is positive x? Negative pi over 4. So again, all we're really looking for with these cofunction identities is to match up the boring side Okay. And then set the arguments equal to each other and solve whatever it takes to solve. Okay, we're going to go back to the sum and difference formulas a little bit and kind of talk about how we get, why this is in the identities chapter, right? Doesn't feel like you were really doing an identity until now. It says, write each function as an expression involving functions of theta alone, meaning we are going to write an identity for this question. We're going to use the sum and difference identities that we already had, and we're going to verify our answers. We're eventually building to the fact that I want us to be able to do an actual verification of an identity using these new rules, essentially. So follow along with me. If we're doing the sine of 30 degrees plus theta, that is the sine with a plus sign in the middle, so we're going to follow the formula. That formula says to do the sine of the first angle multiplied by the cosine of the second angle plus the cosine of the first angle and the sine of the second angle. I've just expanded it so far. Now, only 2 of these 4 functions do we know along the unit circle. But let's go ahead and evaluate them. With your unit circle, what is the what is the sine of 30? 1/2. So we have 1/2 times the cosine of pi. What is the cosine of 30 degrees? Square root of 3 over 2 times the sine of theta. So look, again, I only was able to evaluate one of the 2 from my unit circle. I need to start condensing this down. I'm going to rewrite this just as a step to maybe help you understand what I'm doing here. Instead of writing 1/2 cosine of theta, I'm just going to write it as cosine of theta divided by 2. And instead of writing square root 3 over 2 times sine of theta, I'm going to do square root of 3 sine of theta all over 2. Why did you think I wanted to write it like this? Now, I've noticed they have the same denominator, which means I can write them just as one fraction. Cosine of theta plus square root 3 sine of theta, all divided by 2. That is a single term involving functions of theta alone. See how this is starting to feel like the identities we did in the first couple units? This is why this is in this chapter. Let's go for tangent, yes? Tangent of 45 degrees minus theta. We have our first angle, we have our second angle. We go to fill out the tangent formula. This formula would be giant divide sign. Tangent of the first angle, same sign, tangent of the second angle, all over 1, opposite sign, tangent of the first angle times tangent of the second angle. But again, only 2 of the 4 trig functions have a number that is plugged in, so we only evaluate 2 of the 4. What is the tangent of 45 degrees? 1. This is going to be 1 minus tangent of theta all over 1 plus 1 times tangent of theta, which, what is 1 times tangent of theta? And we're done. 1 minus tan of theta over 1 plus tangent of theta. Ta-da. Yeah, that middle step seems useless, I know, but later on somebody would be like, where did that 1 go? And I'd be like, oh, we multiplied it. So, look, I showed you. Yes? Oh. One more?
No.
Too bad.
It's always hopeful that one day I'd just let it go, right? You can. I know, I'm sorry. So this is the sign of the difference. The formula is sine of the first angle, cosine of the second angle, same sign. Cosine of the first angle, sine of the second angle. Now again, 2 of the 4 functions have numbers plugged in that we can evaluate from my unit circle. What is the sine of 180 degrees? 0. Okay, 0 times the cosine of theta minus, and what is the cosine of 180 degrees? -1 times the sine of theta. Whole lot's going to happen really quickly. What is 0 times cosine of theta?
0.
What is -1 times sine?
Sine
Sine of theta.
Oh.
That's it.
If all of them were like this,
Because you have a negative, negative. Negative times negative is positive. So positive 1 times sine is just sine.
Mr. Fair.
This next problem, I don't know why, honestly, why it was separated from the other ones. It's asking you to do the same thing on this next page. It says to write cosine of 180 degrees minus theta as a trig function of theta alone. That was the same instructions we had before. I don't know why it's a separate example. It's the same thing. Do y'all want to try it on your own or you want me to do it?
no,
Yeah.
Okay.
no.
You're going to have to help me though.
Oh.
Cosine.
Uh-huh.
What
Okay.
formula do I use for cosines?
It's the flip one, right?
Yes.
Okay.
So it's cosine of the first angle. What next?
Cosine of the second.
Cosine of theta. Minus or plus?
Plus
Plus, and then what?
sine of 180.
And
Sine of theta.
I thought it was sine B and sine A.
technically is multiplication can happen in any order. That is what your book has this formula down, so we're going to leave it like that, but multiplication can happen in any order. Cool. Unit circle moment. What is the cosine of 180 degrees? Negative 1. What is the sine of 180 degrees? So a lot of things happen at once. What is it? What happens, I guess I should say.
It's, yeah. And then it's negative cosine.
And then it ends up just being negative cosine of theta. Very good. Nice.
This stuff?
Are you ready?
No. Something like this.
Suppose, I would use your small handwriting here. Suppose that sine of s is 3 over 5 and cosine of t is negative 12 over 13. Both s and t are in quadrant 2. Find the cosine of s plus t. Here's some things that I know. I know that if the end goal is for me to find the cosine of s plus t, I have a formula for that. It would be the cosine of s times the cosine of t minus the sine of s times the sine of t, or vice versa. I just can't get myself to do the order that your book says. Unfortunately for the s's and t's, it looks like the word cost. It's not. It's cosine of t. Okay, cool. Automatically from this problem, I already know that the sine of s is 3 over 5. And that the cosine of t,
Could we not just put the numbers in here? Or no?
what do you mean?
Like, wait, like the S is going out for 3 over 5 and like the T is going for 4.
I like where your brain's at, but do I know cosine of s? So I'm going to put a little placeholder right here. I'm going to put cosine of s back. But cosine of t, I do know that one, right? That's negative 12 over 13. I also know that cosine of s is 3 over 5. But do I know sine of t? No. So I like where your brain's at, that if you're like, you have the numbers, plug them in. True. We just don't have all the numbers. Yikes. Except if you think back to chapter 1,
Oh.
when we did chapter 1, and I gave you 2 of the following 3 pieces of information, you could use Pythagorean theorem to solve for the other one. So we're going to do the following. We're going to say for s, we need an x, we need a y, we need an r. Which 2 were we given if we were given the sine of s?
Opposite and hypotenuse.
Opposite and hypotenuse, and if that's x, y's, and r's, which 2 are those? Hypotenuse is r. I'll give you that one. So that means r is 5. Is sine y over r or x over r? Y over r. So we were given that y is 3, r is 5. How do we find s? Pythagorean theorem. This is going to be the square root of r squared minus y squared. That's 25 minus 9. 25 minus 9 is 16. No rest for the weary. Square root of 16 is 4.
Yeah, go ahead and give me the 0. I'm done.
No, you got it. You got it. You got it. You got it. It's Pythagorean theorem. Here's the only thing, though. It does say that this is in quadrant 2. If we think about quadrant 2, the x's are all going to be negative.
Yeah.
So that actually means that this is -4. Okay. Follow with me again. Let's say we have t this time. If they gave us that the cosine of t is -12/13, which two numbers did they give us? X, y, or r?
R and
R and x. So this is -12 and this is 13.
and then the same thing.
Solve for y. If you know your Pythagorean triples, by the way,
Triples.
Pythagorean triples, those are things you can memorize so you don't have to do Pythagorean theorem. 3, 4, 5 is a Pythagorean triple. 5, 12, 13 is a Pythagorean triple.
Really?
Yeah.
Wait.
If you don't trust me?
Yeah.
Yeah, you don't trust me?
I don't trust you.
13 squared minus -12 squared. 13 squared is 169. 12 squared is 144. That is, my brain is looking at the wrong example. 25, thank you, yes. Which is 5. So now that we know this, though, Genesis's idea from the beginning is, can't we just put the numbers in? Now we can, because we have x, y, and r for all of these things. The cosine of s, we look at s, cosine is x over r, which means this is -4/5. And the sine of t, now we look at t, sine is y over r, which means that this is going to be 5/13. Fraction moment, -4 times -12 is +48. 5 times 13 is 65. 3 times 5 is 15, and 5 times 13 is 65. 48/65 minus 15/65. 33/65. That's, yeah, we did it.
I don't want to do this anymore.
Well, there's one more.
Can I drop out?
Wait, is this still the drop period?
No,
You're laughing.
Why?
no, you're fine.
Literally.
You're fine.
No.
It's fine.
This is gonna fail. It's fine.
No, you're fine.
I'm gonna fail.
It just took, yeah. I'm here
Oh
because I
my
chose to be
goodness.
here.
Can we do it again?
When am I ever gonna use this in cybersecurity?
It depends on what you do with your life. But either way, you're learning problem-solving skills and you're learning how to do hard things. That you will use your entire life.
How am I gonna get triggered in cybersecurity?
I'm just going to smile over here while you guys cry.
When am I ever gonna use sine, cosine, and tangent?
Depends on what you do with your life.
Cybersecurity.
Honestly, that's very technical. You probably will.
Oh my! I swear, if I do, I'm gonna change jobs.
Okay. Example 6. Stay with me. We can do it. Suppose that A and B are angles in standard positions such that sine of A is 4/5 between pi/2 and pi, and cosine of B is -5/13 between pi and 3pi/2. This is a really fancy way of saying this one, my marker is not working, is in quadrant 2, and this one is in quadrant 3. Okay. Find each of the following. We're going to do both the sine of A plus B and the tangent of A plus B. So just like before, I know we're going to need the x, y, and r for both angle A and angle B. Let's look at A. For angle A, we know we're in quadrant 2. We need x, y, and r. Which two of the three did they give us already? If they gave me sine of A is 4/5.
Oh, x. No, y.
Y and R, and if you remember those Pythagorean triples, what was the other number that went with 4 and 5? 3. If you didn't know that, use Pythagorean theorem. Just to save myself space, I'm going to go B right here. Quadrant, or B, oh wait. Whoa, Miss Quigley, back up. I just said it's in quadrant 2 for A. Which one of those letters should be negative? X should be negative. if they told me that for angle B, that the cosine of B is negative 5 over 12, that means I know that y is negative 5,
Why is it?
x is negative 5, and r is 13. What was the number that went with that triple? 12. In quadrant 3, does it need to be positive or negative? Negative. Okay. So those triples come in handy. Now we have everything we need to answer this question. We do. Sine of A plus B. If I use the formula from the front of your page,
Yeah.
it's sine of A times the cosine of B plus the cosine of A times the sine of B.
Okay.
What is the sine of A?
Very question. Oh, it's 4 over 5.
4 over 5. What is the cosine of B?
Cosine is negative 5.
Fabulous. And now we have to use the x, y, and r that we found. What is the cosine of A? Cosine is x over r, negative 3 over 5. And then the sine of B, there it is, negative 12 over 13.
Okay.
Fraction moment.
Yay.
Top times top, bottom times bottom. This becomes negative 20 over 65. Minus, negative times negative is positive.
Yeah.
That's 36 over, what, 65? Which gives me 16 over 65. Yes. Now don't flip it yet. We still got one more on this page. Because I also want to know the tangent of A plus B.
Oh, joy.
So we need the formula for tangent. We do. Formula for tangent. This is the tangent of A plus the tangent of B, all divided by 1 minus the tangent of A times the tangent of B. We're going to put some fractions and fractions here. Are you ready?
No.
We're doing it anyways. The tangent of A. Tangent is y over x.
Okay.
So what is the tangent of A?
4 over 5. No, 4 over negative.
4 over negative 3. Tangent of B. Again, y over x.
My reaction is negative 12 over negative 5.
Okay, and all of that is over 1 minus those same numbers multiplied together. 4 over negative 3 times negative 12 over negative 5.
Ew.
So that numerator, I'm adding fractions together. What do fractions have to add them together? Common denominator. So if I make this a denominator of 15, that was times 5. So I'm going to make the top negative 20. I'm just transferring that negative to the top to get it out of the denominator, right? For 12 over 5, negative, negative, they cancel out, yes?
Yeah.
That denominator, if I make it 15, that's times 3, which means this is 36. Top times top, bottom times bottom for the bottom. 4 times negative 12 is negative 48. Negative 3 times negative 5 is 15. Ugh, I have a minus though. Can I just change that? What is minus a minus? Plus. So I'm just going to change that to a plus just to clear some things up. Okay, so that numerator I can actually add. Negative 20 plus 36 is 16 over 15. But can I add that denominator yet? No, because what do they have to have? Yikes. So we're going to change 1 to 15 over 15. So I can add it with 48 over 15. Which means I get, stick with me, 63 over 15. 15 plus 48 is 63. Yikes, but then I have a fraction divided by a fraction. What do we do? Keep, change. The anger of how you said keep, change, flip with. But look how nice this is. This is so satisfying. Watch.
No, it's not.
The 15s cancel out. It's just 16 over 63.
Is that it? Thank God.
Can we not do the back?
We are going to do the back page.
Yeah, it is.
So no homework time around.
Miss.
Welcome back from spring break, everybody.
Miss, it's Monday.
True?
I should work you this hard
True.
on Monday.
So now we're back to identities.
Oh my God.
Yeah, you remember last class when we verified those identities and I gave you
No.
the question and I needed you to make one side look like the other side?
Miss, my mom and
Oh, wait, I do.
We're doing that here. Last class when we did this, I asked you to start with the more complicated side. Which side here is more complicated? Left side, I agree. So we're going to start with this left side and we're going to do things and give a reason for each step as we go to get it to look like the other side. We've arrived back at identities.
Miss, math is the reason.
You'll be fine. Here's what we're going to do. We're going to first start with the reciprocal identity because I have no cofunction identities or sum and difference identities for secant, cosecant, or cotangent. I only have them for the three normals. So in which case, I can rewrite this as 1 over the cosine of 3 pi over 2 minus x. That is the reciprocal identity. Do we follow so far?
Sure.
Thank you. Secant and cosine are reciprocals. We can still use this reciprocal identity.
Oh.
Then I can go to my sum and difference identities. Because I'm subtracting these two numbers inside of a cosine function, I can use the sum, just kidding, the differences of cosines, which would be the cosine of the first angle times the cosine of the second angle plus the sine of the first angle and the sine of the second angle.
Okay, what?
That is the sum or difference identity. That's the identity we learned at the very beginning of today.
Miss, it was so easy.
I know.
In the beginning.
Too easy.
No.
But hey, look, you have numbers inside of a sine or a cosine. Those numbers are from our unit circle. What is the cosine of 3 pi over 2?
3 pi over 2?
What is the cosine of 3 pi over 2? It's 0. And then what is the sine of 3 pi over 2? Negative 1. This step, when you're actually looking at your unit circle, we're going to call that evaluate. Mathematically, that's what we would be calling it. We are evaluating those functions. Ooh, but then I have 0 times cosine of x. What is 0 times anything?
0.
Canceled. So then I have 1 over negative sine of x. That's my cancel step. And then, yes, we recognize 1 over sine can be rewritten as negative cosecant. So that's, again, my reciprocal identity. And that's where I'm done, because that's what I wanted.
I hate science.
Last one.
Thumbs up, miss.
Then we'll go back to all the places that I lost people, because we've all made eye contact. I know. This is the most complicated side. Do you agree?
Well, sure.
What's happening on this side?
A lot of things.
True. Give me one of those a lot of things.
The sine of...
Sine
Yeah.
of,
5%.
oh, so a sum of sines. So if I'm adding two things inside of a sine function, that's the sum of sines. I'm going to use the sum identity. What's happening in the second one?
Cosine.
Cosine of a sum. I'm adding them together. So I can also use the cosine identity.
This is going to be a lot of...
Yes,
Like one long thing.
it is.
Oh.
For the first part only, the sine of pi over 6 plus theta. That can expand to sine of pi over 6 cosine of theta plus cosine of pi over 6 sine of theta. That second part with the cosine becomes cosine of pi over 3 cosine of theta plus or minus. minus sine of pi over 3 sine of theta. And that is your sum and difference identities times 2. Let me write that where you can see that. We just did the sum and difference identity twice. There's a whole bunch of angles plugged into trig functions. Look at your unit circle. What is the sine of pi over 6? 1 over 2, so then I have 1/2 cosine of theta. What is the cosine of pi over 6? Square root of 3 over 2 times the sine of theta. And then I have cosine of pi over 3. That's 1/2 times the cosine of theta. And then square root of 3 over 2 times the sine of theta. So what is that step called when I'm looking at my unit circle?
Looking at unit circle?
I mean, yes. It starts with an E is the word I'm looking for. Evaluate. Yeah, heard you. Thank you. What do you notice? True. Good idea. What else do we notice? There's something nice that's going to happen. Cancel the signs. One of them's positive, one of them's negative, yes? Positive square root 3 over 2 sine of theta and negative square root 3 over 2 sine of theta cancel out. And then, like Joseph saw, because they have the same denominator, let's go ahead and write them where it's maybe easier to see that we can add them together. So that was my cancel step. We write them as one denominator. What's cosine plus cosine? Oh, that's times. 2 cosines of theta. Kind of like x plus x is 2x. So cosine plus cosine is 2 cosine. That's an add step. What do you notice? Cancel out the 2's. What am I left with? And that's what I wanted. Yes. 100%, yeah. Half plus half is a whole.
Yeah.
So you could have seen it there. Like I said, there's more than one way to solve these problems.
Okay, so now we're done?
So now we're done. Listen, I know that this was a lot. I know this was hard. It's very detail-oriented. Check those formulas and work them slowly.
So